Hello everyone, welcome to Unravel Logic channel. In today's video, we'll be covering the concept of covariance. It is a very powerful but often misunderstood statistical concept. So let's understand this in today's video. Covariance. So let us start with the definition first, as usual. Covariance is a statistical measure that describes the direction of a linear relationship between two variables. Okay, so covariance is a statistical measure that describes the direction. This is the important word here. Okay, the word to note is direction of linear, another important word, linear relationship between two variables. Okay, so what this means is that you don't really know yet that whether the two variables or what is the relationship between these two variables. Okay, whether they are both increasing together, whether one is increasing or one is decreasing, whether uh, they are both consistently increasing or consistently decreasing. Okay, or whether they are both decreasing together. So this is what you're trying to find out when you are using the concept of covariance. Okay, and another thing to note here is that we are talking about a linear relationship. Okay, so the relationship shouldn't be a curve. Okay, it should not be like this, it should be either like this, it should be either like this. Okay, or like this or this or this. Okay, another thing to note here is that, and this is very important. Okay, is that the correlation does not show the strength, does not show the strength or cause of the relationship. It only shows the direction. Okay, does not show the strength or cause, only shows the direction. When we say strength, we mean that if two variables, whether the two variables are strongly moving together or not, or whether one variable is causing another variable. That is what we mean by strength or cause. Okay, it does not show it. Covariance does not show the strength or cause, it only shows the direction. Whether if one variable is increasing, another is also increasing, if one variable is decreasing, another is also decreasing, or if either of the variable is increasing and another is decreasing. Okay, that is the direction it shows. Now the next thing that we'll look at is the formula. So what I'm trying to do is I'm trying to get the formal definition and formula out of the way, and then we'll actually understand this concept in detail with an example and with intuition and everything. Okay, but for first, let's get the mathematical formula out of the way, and we'll also understand how that mathematical formula or what are all the components in that mathematical formula does or do. Okay, so this is the formula. We write this as covariance or co of x comma y, which equals 1 over n, that is summation from I equal to 1 to n, where we simply multiply the difference of xi minus x bar, difference of xi and x bar, and difference of yi and y bar. So let us understand what each term means. So this is number of data points. This is ith data point for x, ith data point for y, and this is mean of x, this is mean of y. So let us understand the intuition behind this formula now. So this term denotes how far the ith value of x is from the mean of x. This is how far the ith value of y is from the mean of y. Now note that we are multiplying the ith difference, okay? Ith difference, okay? Which means that the corresponding x is this far from the mean of x, okay, and the corresponding y is this far from the mean of y, the same ith value, okay, same I. All right, now this is basically telling us that how these 2 points are varying given the same I from their mean. If they both are going up, if one is going down, one is going up, if both are going down, okay, or if this one is going up and this one is going down, this is what this will tell us, okay. So which means that, for example, for xi minus x bar, we might get something negative. For yi minus y bar, we might get something positive, okay. This is what this up down and up down means, okay. So when we say up, we mean positive. When we say down, we mean negative, okay. So negative, positive, 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 negative, or negative, negative, right? So we'll get a some sign here, okay, which is nothing but direction, okay. Now why are we multiplying this? Why are we multiplying these differences from the mean? Okay, the reason behind that is that we need to find the combined direction, okay. So for example, if one is negative, another is positive, the combined direction is negative, okay. It's normal arithmetic, simple arithmetic. So if both are positive, the combined direction is positive. If this one is positive and this one is negative, the combined direction is negative, okay. And if both are negative, the combined direction is positive, okay. So this is saying that the variables are moving together at this ith point. Okay, this is also saying that the variables are moving together at this ith point, and this is saying the opposite. Okay, that the variables are not moving together. Okay, yeah. Now, why we are summing this? Okay, we are summing to total across all data points. Okay, and why we are dividing by n? Because we want to find the average. Okay, to find the average. So basically what we are trying to do is we are trying to find the average direction of both the variables together. Okay, trying to find the average direction of both the variables. Okay, so if most of the deviations, when we say deviations we mean these, if most of the deviations are in the same direction, it means positive covariance. If the deviations are in opposite directions, it means that the covariance is negative. Okay, and if there is zero covariance, it means that there is no pattern, which means that the two variables are not moving together anywhere. Okay, so now let us understand this concept with a real life example. Let us say students recorded how many hours they studied and what scores they got. Let us say students recorded hours studied versus exam scores. Okay, let us quickly see the data. So we have student here, then study hours, which will be X, and then exam score, this will be Y. So this is the data that we have. We have 5 students and the hours studied, which is 2, 4, 6, 8, 10, and the exam scores. Okay, so when we calculate the covariance of this data set, we'll get a positive value indicating a positive relationship or positive direction of the movement of these variables. What we mean is that as the study hours increase, the exam scores also increase. We can clearly see with the data because this data is kind of sorted. Okay, so if you see, the student who studied only 2 hours got 60 marks, and the student who studied 10 hours got 95 marks, which is the maximum, and then 4, 6 and 8 respectively got 70, 80 and 90 marks. Okay, so you can use the formula and you will get a similar result, okay, which will tell you that the covariance is positive. Okay, let's do it. Okay, let's calculate it using the formula. Okay, let me calculate. So this is how we calculated the covariance as per the formula that we just studied. So we calculated the x bar first, which is the mean of x. Then we calculated the y bar, which is the mean of y, and then we put everything into the formula. We multiplied the differences for each data point from their mean, and then summed all of them together, and then divided that by the number of data points, which is 5, and we got the covariance as 36. So let me write here co x comma y equal to 36. Now how to interpret this value? Okay, so this actual value, which is 36, doesn't really matter. Okay, so magnitude doesn't matter. What matters is that whether this is positive or negative. So if this is positive, which this is, it means that there is some relationship between the study hours and exam scores which is positive. So we are looking at a positive relationship, which means that in this data set for which we found or calculated the covariance, if the study hours are increased, exam scores will also increase. This is what it is telling us. Okay. However, it is not telling us that if you study more, your exam score will be more. Okay, it is just telling that for this particular data, this is what it has found, that if a student studied more, they scored more in that exam. But this is not telling us that if a student will study more, they will get a better exam score. Okay, there is a difference. I hope you understood this. Okay, so this is not predicting or foretelling. This is just saying that for this data, this is the relationship between these two. Okay, so now let us see some properties of covariance. Okay, we'll see these properties quickly because you can yourself try this. Okay, because now you have understood the concept, you understood the formula. Okay, so I won't deep dive too much into this. So covariance is symmetric. Okay, in the sense that covariance of x comma y equals covariance of y comma x. Okay, because you are just multiplying, so it doesn't matter which term you multiply first. Okay, it is linear. Okay, I'm sorry, linear. What this means is that covariance of ax comma by, so a and b are constants here, is equal to, if you simply took out the constants, because ultimately you are multiplying both the terms, yeah, so you can simply take out the constants, and you can try this out as well. Okay, by applying all these things in a formula, and you would understand what we're trying to say here. And if you find the covariance of the same variable with itself, you simply get the variance of x. Okay, because self covariance is just variance. Okay, how is this? It's very simple. If you simply put in the formula, okay, so I equal to 1 to n, and then you'd simply do xi minus x bar and then xi minus x bar, because the other variable is also x, right? So you would simply end up getting as this is squared. Okay, so if I remove this, yeah, and this is nothing but variance of x. This is not normalized. What I mean is that this 36 has no value. Magnitude doesn't really matter. So this is what we mean when we say it is not normalized, and it simply depends on units. Okay, if the units are same, the interpretation would be better. Okay, depends on units. Can be positive, negative, or zero. So can be positive, negative, or zero. Okay, we already discussed this. And now the next is why use covariance. Okay, why to use? The simplest answer is to understand or detect the directional relationships. Okay, to detect directional relationships. To detect directional relationships. Okay, positive, negative. Detect means we already do not know this mathematically. We probably have an intuition, but we want to prove it mathematically, so that's the reason we use the word detect. Directional is positive or negative, as we already discussed. And this is like the first step to understand correlation. Okay, so first step to understand correlation. We'll cover this in the next video. You will get a better understanding, and there we'll use the concept of covariance before we understand the concept of correlation. And then when to use, so you can simply use it during exploratory data analysis. So when to use in exploratory data analysis. So you're just simply exploring the data, right? So you take, for example, if you have 10 variables, so you would take any two variables for which you have some intuition, and then you try to prove that intuition by calculating, mean, median, standard deviation, variance, covariance, right? So you would understand that whether these two variables are related to each other in any way. So you would use covariance on those two variables and calculate it, and then understand whether the variables are moving in a positive direction or not. If they are moving in a positive direction, or if they are moving in a negative direction together, which means there is a covariance, then you would go on to find out the correlation between those two variables, which would cover in the next video. But yeah, you can simply use covariance in the exploratory data analysis. Okay. When not to use, this is also important. When not to use, so you should not use it when you want to interpret cause effect. Yeah. So let us understand what I mean when I say cause effect. Okay. So let us understand that, let us assume that we have some data wherein we are analyzing ice cream sales versus drowning data. Okay. And when you calculated the covariance, it turns out that the covariance between ice cream sales and drowning data is positive. Now, in most cases or most people, they would conclude that when people are eating more ice cream, people are drowning more. Okay, but that is incorrect. That is what cause effect is. That people eating more ice cream is causing people to drown. Okay, which is the effect. Okay, all right. So this is incorrect assumption, or this is incorrect interpretation. To truly understand why people are drowning more when the ice cream sales are high, you would also need the data on temperature or more data about these two things. Okay, so for example, if it's the summer season, which it would be, because in summer season ice cream sales are high. Okay, people would tend to, swim more because it's summer. They want to be in water, they want to go swimming more, right? And because they are swimming more, they are drowning more. Okay, so you need to understand more variables. You need to understand that more variables are at play here. For example, what is the season? Okay, are people swimming more? Okay, if you do not have access to this data or more data, okay, then you cannot simply conclude just by seeing covariance, which is positive, that these two variables are related to each other, that eating more ice cream or increasing ice cream sales is causing people to drown. That is the incorrect interpretation. Okay, this is what we mean when we say cause effect. Okay, so you should not use covariance to interpret cause effect relationship. Okay, yeah. For that you will need correlation, again, which we'll study in our next lecture. Lastly, let us understand correlation by looking at the plot of our example, which is the study hours and the marks in exam. Okay, so I will show you the plot now. So look at this plot here. Okay, so on the x-axis we have study hours, on the y-axis we have the exam scores. Now this is the mean. For exam score, this is mean for study hours. Now you can see how far each point is from each of the mean. Okay, so for example, if you see study hours, okay, then this is the mean, like 6 hours is the mean. Okay, and you can see that this particular point, which is 2, is this far, okay, from the mean. Okay, which is like 4 hours. Okay, and this is 2 hours far from the mean. Okay, and similarly you can see the distances, same distances here as well. Okay, so this plot is showing us that these are the differences, and then you multiply these and then you see this line, okay, which is the actual correlation, this line. Okay, how each points are correlated and how is it positive. Okay, so this is visual representation of the fact that there is some uh, covariance between the study hours and the exam scores. I mistakenly said correlation earlier, but what I meant to say is that this is covariance. This represents covariance between these two variables, and it shows that the covariance is positive because you see the slope of this line, or this line is increasing as the study hours increase, because with the study hours the scores are also increasing, so this line is effectively increasing. Okay, hence this is the visual representation of covariance between study hours and the exam scores. So I think that is it for today's video, and if you found this helpful, please hit that like button, subscribe for more data science explanations, and comment your favorite example of misleading correlation or covariance. Okay, so just like the example that we saw, right, the example of ice cream sales versus drowning data. So comment such an example if you have, and yeah, see you in the next video. Thank you.